About the diode, forward bias, reverse bias. We have two problems there. Today also we'll start the session with one problem and we'll switch to the application of diode. Okay. Let's take one example. The question is given. Let me take it for a minute. The question is given as you have diode circuits like this, they are connected. These are the three diodes. Let's take D1, D2 and D3. Okay. The positive terminal or the anode of the diodes are connected with, this is plus 3 volt, this is plus 2 volt and this is plus 1 volt. Okay. Here they are connected with resistance 1K value and it's grounded. Here they are taking output and let me draw the output different color. This is the output and this is the current. Okay. Now question is, if D1 and D2 and D3 they are ideal diodes, D1, D2 and D3 they are ideal. Okay. Consider them ideal. Okay. Now the question is, find out I and V. You have to find I and V naught. Okay. So how you will solve this type of circuit? See, D1, D2, D3 they are connected parallel to each other and positive terminal of D1 assigned with 3 volt and the positive terminal of D2 will be having 2 volt and D3 having 1 volt. So friends, let's take condition. Suppose D3 in forward bias. D3 in forward bias. So here the voltage will be 1 volt. Okay. So because of this 1 volt and this D2 will be also on, D1 will be also on, situation will be like 3 volt and this is point, 2 volt, this is point and 1 volt, this is point. So this is faulty condition in circuit. This condition can't be happen, means at particular node will be having only 1 voltage. In this case, at this node A you are having 3 volt also, 2 volt also, 1 volt. Is it not? This condition is not possible. Okay. At single node, you can be with only 1 volt. It's like, see, it's similar to you are having one circuit. In that circuit, you are having 3 ampere. In that circuit, you are having 1 ampere. In that circuit, you are having 9 ampere. Is it possible? No, this is not possible. Okay. In single branch, you can have only one current. Similarly, at single node, you can have only 1 volt, right? So this condition is fault condition. Now come to the next one. Assume D2 is on and the remaining, we'll check the remaining one. Okay. My condition is D2 is on. If D2 is on means forward bias, here the voltage will be 2 volt. Because of this 2 volt, the D3 will be off, but D1 will be on. So in that case, the condition will be like, this will be on 3 volt, this is also on 2 volt, and here this is the point, and again at the point you are getting 2 voltages, 3 volt and 2 voltages. This is faulty condition. It can't be possible. Okay. So again, this assumption is also wrong. Come to the next one, and in the next one, you have to assume D1 on, and let's check the condition. Okay. Let me remove this also. Now your condition is D1 is on. If D1 is on, forward bias, the node over here voltage is 3 volt. Once the A is 3 volt, the D2 will be off because D2 will be reverse bias. This is 3 volt, negative terminal, positive terminal 2 volt, D2 will be off. What about D3? It will also off. Now we are having only single node and single voltage, that is 3 volt. So what is the value of V naught? V naught is nothing but 3 volt. It's very easy problem. Now they're asking for the I also. Can you find this I for me? It's very easy. I is nothing but the voltage difference divided by resistance. Voltage is 3. Voltage difference is 3 minus 0 divided by 1K. Your current is 3 milliampere. Is it okay? So this is the question. I'll take another example. In this question, you have plus 5 volt over here connected with resistor 1K. In this 1K, the current I is given, and connected with, or at this node we are taking V0. Here you have 3 diodes like this. Again they are parallel diodes. 3 diodes, D1, D2 and D3. Let's connect it like this. Again this is plus 3 volt, this is plus 2 volt and this is plus 1 volt. Okay. This is the circuit given, and these 3 diodes are ideal diodes. Let's take it D1, D2 and D3. Now the question is find out V0. Find out V0 and I. This is your question. Okay. Now again, approximation method. You have to choose. Let me change it. Change the color of it. Okay, fine. See, if now suppose 3 volt or D1 is on. Suppose, let's take D1 is on. If D1 will be on, what will be the condition? This volt will be 3 volt. Is it okay? If D1 is on, means short circuit, the node A will be 3 volt. If 3 volt is this voltage, in that condition, D1 will also work because D2 will become in forward bias. Here the voltage is 3 volt. Here the voltage is 2 volt. It will be also on. What about this D3? It will also on. So condition will be like this is your condition. This is faulty condition. 3 volt, 2 volt, 1 volt. Okay, this is faulty condition in circuit. At particular node, only single voltage can exist, not more than that. Okay. So if you will choose D1 on, you will get fault condition. If you will choose D2 on, again you will get fault condition. So you have to choose that your D3 is on. Let me erase it first. Okay. Now I'll choose D3 is on. If D3 is on, here the voltage is 1 volt. Now check what is the condition of D2. Here it's 1 volt and at the negative terminal it's 2 volt. It will be definitely will not work. What about D1? This one is also not work because here the voltage is 1 volt now. In the negative terminal it's 3 volt. Definitely it will be in reverse bias and will not conduct any current in the circuit. Now in your hand you are having the proper, perfect and very correct 1 volt voltage at the node A, and this 1 volt is nothing but the V0. So V0 value you find out, and that is 1 volt. What about the current? You have the potential difference, so you can easily find out this current. This is 5 minus 1 volt divided by 1K. So 4 divided by 1K, your current is 4 milliampere. So this is all about the diode problems. I think the diode concept is pretty clear to you. Now we'll switch to the next topic. Okay. Let's come to the next topic, and that is the application of diode, right? Where we are using this diode. We have seen the diode. This is the symbol. This is the P region, N region. The P region I call the anode, N region I call cathode, right? So where we are going to use this diode? Earlier we have discussed that diode is used in rectification also. So how it rectify? So first application of the diode, we'll see the half wave rectifier. Half wave rectifier. Actually in the half wave, as the name suggests, means at the output stage you will get something. You are getting wave, but that wave is half. See, if at the input stage, what is the output of this half wave rectifier? I'll consider first, then I'll go to the half wave rectifier. If you apply the input Vm sin omega t, see this is the sine wave, At the output stage, you will get the half of that wave. Means some part of this initial or input wave will be gone out. Okay, so this is the half wave. Here we will not get the full wave. Here we will get the half wave. That's why we are calling it the half wave rectification. And this thing is nothing but the rectification, means you are removing something. Okay. So in positive half cycle, let me start it with, first erase it. In positive half cycle, see, this is the circuit of half wave rectifier. One diode. See, this is the diode is connected in the circuit in series with R. At the R output stage, I am taking V0, and here this is the input stage, and the input is Vm sin omega t. Definitely this is the sine wave, so graph of the Vm sin omega t is like this, Vm sin omega t. This is given over here. Now this is the transformer kind of thing. Actually, this is the application. We don't have mean with this transformer. Today we are considering only this half wave rectification. So let me tell you briefly about this. We'll apply the input over here and we'll get the output over here by linking of the flux between these two coils. Remember, we have seen in the circuit theory mutual inductance and something. So because of this phenomenon, mutual inductance, the voltage of the primary will be linked with the secondary. Okay. So why we are using this then? We are using it because we can improve the quality, means we can it step up or step down. Okay. It is based on our requirement. So this is not part of our study. The part of our study is only this. The input you applied is over here Vm sin omega t. Now what will happen? Tell me. See, in the positive half cycle, this is your input wave, suppose, positive and negative. The time period is given 2 pi. Here is your diode. Okay. In the positive half cycle, the diode will be biased like this. Which type of biasing is this? This is forward bias. In the forward bias, diode will work as short circuit. If this diode will be short circuit, so this entire input will come to the output. In this case, in the positive half cycle, positive half, the V0 will be nothing but Vin. Whatever input is there, same will reflect at the output. And we consider the diode is ideal. But if the diode, in practical, there will be drop 0.7 cut-in voltage. Remember, this is the barrier potential offered by the diode in the circuit. But for the time being, we are considering the ideal diode. So in the ideal diode, it will be short. So entire input reflect to the output, and at the output stage, V0 will be Vin. But what about the negative half? In the negative half, the diode will be facing the voltage polarity like this. In that case, the diode will be open circuit. This is the reverse biasing we have done in the first video. So the diode will be off. Here in this circuit, if diode will be off, will there any input will be linked with over here? No, there will be no voltage linked to output V0. In this case, V0 will be definitely 0 volt. 0 volt means in this region you will get the output 0. Now see, this is the half wave rectification. In the positive terminal or positive half of the cycle, you are getting output V0 similar to input. In the negative half cycle, you are getting 0 at the output stage. So this is the story of one cycle. This will repeat over to the cycles, next cycle, and similarly you will get half wave like this. This is the half wave. So you are applying the full wave, you are getting the half wave. Maybe you are having some requirement or some need based on this half wave. That's why you are rectifying it. And I'm calling it the half wave rectifier. Is it okay? So in the positive half cycle, D is forward bias and conducts. Thus the output voltage is same as the input voltage, and the negative half cycle D is reverse bias, and therefore output voltage is 0. The output voltage form is shown in the figure. Now this waveform is shown in the figure. Now we have to calculate the effective value of this. You calculated output, okay, it's very good to you, but now you have to given the effective value of this, right? We note effective value, the average value you will give for this. For this input you can't give the average value, because in the one cycle you are having positive cycle equal to the negative cycle. They will cancel to each other, you will get zero average value. So for any sine wave or cosine wave, the effective value will be the RMS value. You have to give the RMS value of any sine wave. But in this case, you can easily find out the I average. So it will be good to find I average or V average. Let's take it V, because we are dealing with the voltage. So we can easily find out the V average. How to find V average? See, V average is nothing but, V average we have to calculate. So summation from 0 to 2 pi, the entire cycle 0 to 2 pi. I'm going to calculate the average for this. This is the cycle 0 to 2 pi. The value of the output V0 dt divided by total time. Total time is 2 pi for this circuit. Is it okay? Now see friends, I can divide this cycle in two parts. One is 0 to pi. In 0 to pi, I am having Vm sin omega t. Similar to input Vm sin omega t dt. But what about the pi to 2 pi? Pi to 2 pi, I am having 0 value. Divide by 2 pi. So you are remained with 1 by 2 pi Vm sin omega t d omega t. Is it okay to you? Now when you will solve this equation, you are integrating this with respect to omega t, because you are considering here omega t. Okay. So when you will differentiate with respect to omega at the output, you are integrating this, right? So when you will integrate, you will get Vm by pi, means 0.318 of Vm. 0.318 of Vm. What it means? It means in the half wave rectification, if originally you have Vm, now your Vm will, or the V average will become Vm 0.318. 31.8% of the Vm you will be having V average in the half wave rectification. So once you find the value of V average, can you find the value of I average? Yes, you can find out. I average is nothing but V average divided by R. V average is Vm by pi into R. So this is Vm by pi R ampere. This is your current value. So please remember this equation. V average for the half wave rectification is 0.318 of Vm, or simply you can say Vm by pi. This is the integration. This is I'm leaving to you as an exercise. Okay, you can solve it at the final stage. You will get this definitely. Now we'll switch to the full wave rectification. What is the full wave rectification? In the full wave, the entire sine wave or input wave will come to the output, but in this way. In the positive half cycle, you will get some output, and the negative half cycle, again you will get some output. We will talk about the half wave rectification. There in the second or negative half cycle, we were getting zero output, but here we'll get something. Is it okay? So how this is going on? See, what is the circuitry? Circuitry is like this. This is the input primary stage. Okay. This is the secondary stage, and the secondary stage is center tape. This is we call the center tape. If we'll center tape it, then only we'll get this type of wave. Otherwise we'll not get it. Okay. So D1 is connected with R and D2 is connected with R same, and here we are taking the output V0. So friends, what will happen in the positive half cycle? See, let me tell you one thing. In the positive half cycle, see here plus minus, it will become here plus minus. Okay, in this minus and plus. Is it okay? The situation is like this. See, a single phase full wave rectifier using center tape transformer. This is the center tape transformer type of circuit, right? It supplies current in both half cycles of input voltage. Okay. In the first half cycle, D1 is forward bias. In the first half cycle, it will be in forward bias, but this will be in reverse bias. Okay. D2 will be reverse bias definitely. So, it will work like in the positive half cycle, D1 will work. In the negative half cycle, D2 will work. In the negative half cycle, this D2 will be in forward bias. Okay, so your output will become positive. See, in the first half cycle, D1 is forward bias and conducts, but D2 is reverse bias and does not conduct. In the second half cycle, D2 is forward bias and conducts, and D1 is reverse bias. It also called two-pulse midpoint converter because it supplies current in both the half cycles. Both the half cycles, this device is producing the current or supplying the current. That's why we are getting output of full wave. Okay. So it supplies in the both half cycles. The output voltage waveform is shown in figure C like this. Wait a minute. So here we are applying the input, right? In the positive terminal over here, the polarity will be like this, and this polarity will be divided over here like plus minus plus minus. Is it okay? So because of this, the diode D1 in the positive half cycle of the input will be in forward bias. See, positive terminal is applied to the diode, so it will be forward bias and will conduct. At the same time, the diode D2 will be turned off. Why? Because this is in reverse bias. In the reverse bias, diode works as an open circuit. So D2 will not conduct, D1 will conduct, and you will get at the output like this. In the negative half cycle, the situation will be, this will be plus, this minus, this plus, and this minus. Okay, here the situation is minus plus. So minus plus will divide into two ways because of this center tapping. Okay. So this center tapping is clearly helpful to get this as the output, right? So in this case, the D2 will be forward bias, and in this forward bias, when this will become short circuit, this entire voltage is again drop like this. Okay. So this and this both are same. So again plus V0. Like this we are getting at the output. Is it clear to you? So the working is pretty clear to you. The waveform is clear to you. Now next stage will be, you have to calculate V average. Okay. The V average of this is, we will talk about the V average. From 0 to 2 pi you will consider it, and 0 to 2 pi you will take, in both cases you are getting Vm sin omega t. Right? You have to integrate it with respect to omega t. Is it okay? So this is the summation or full value divided by the period, and that is 2 pi. Okay. Or for this waveform, the period is 0 to pi, 0 to pi, 0 to pi. So we can consider only 0 to, it's 0 to pi only, and this is pi only, right? So 1 by pi and 0 to pi Vm sin omega t d omega t. When you will simplify this, you will get the Vm is constant, right? So you will get 2 Vm by pi, double of whatever we were getting in the half wave. So V average is nothing but 2 Vm by pi. It is like 0.637 of Vm. Okay, please remember this. This one is very important. Sometimes directly we have to use it. So in full wave rectifier, the average output voltage is given by 2 Vm by pi. Is it okay? So if you get the V average, you can easily get the I average also, because the situation is like you are having R. Across this R, you calculated V average. Across this R, you calculated V average. So it is easy to find I average, because I average across this R or in this R is nothing but V average divided by R. Is it okay? V average you calculated 2 Vm by R. So this is ampere. So 2 Vm by pi R, 1 pi I forgot here. So this is okay. Last time in the half wave rectification you have find, let me clearly mention over here, in the half wave the wave was like this, 0 to pi, 2 pi, this is Vm. Okay, so for half wave V average is 0.317 of maximum value. If instead of this you have full wave, if you have full wave 0 to pi, 2 pi, 3 pi and so on, in this case V average will be just double of it, 6.634 of Vm. Is it okay? Or in another way you can remember this like Vm by pi in the half wave, and in this case it will be 2 Vm by pi. I hope this is clear to you. So this is one of the application of diode in rectification. You have seen full wave rectifier, you have seen the half wave rectifier. Now we'll move to the bridge rectifier. So what is the circuitry of bridge rectifier? In the bridge rectifier, we are using the bridge rectifier as the full wave rectification. See, you can see like this. Okay. So this is the circuitry of bridge rectifier, and in the bridge rectifier, see, we are getting this type of situation or circuitry. This is like making bridge. That's why we are calling it the bridge, and the work of this is nothing but the full wave rectification. Full wave rectification, so we are calling it rectifier, and bridge we are calling because we are using the bridge circuitry over here. At the input stage in the primary, you applied the input. There is no center tape. The working of center or the function of center tape is replaced by this bridge over here. Okay, so entire input you will get in the secondary stage, and now come over here. The positive cycle, if I'll consider first, the positive cycle of the input, you have to consider, you will get, if this is positive, D1 is off. What about D? This is D2 and this is D1. Let me check the circuit. So here is little bit mistake. You have to change it, this diode like this, and this diode also like this. Okay, this is the diode. Now see, in the positive half cycle, what will happen? When in the positive half cycle, here is the voltage is positive. Who will be in forward bias? Yes, D1 is forward bias. Okay. Wait a minute. D1 is forward bias. So current will go to the D1. Now here the current will go to this side because this D2 will be in reverse bias. This terminal is at higher potential. So this will be reverse bias. The current will go to R, and from R it will move like this. Over here you will get this as, so at this stage current will not go at this because this one is at higher potential. So current will go into this and it will come to this. So this is the positive half cycle. In the positive half cycle, the current direction is this. So you'll get the voltage drop here in this direction. Is it okay? Come to the negative half cycle. In the negative half cycle, what will happen? Let me clear it. And you have to change the polarity of this too. You have to change it, right? Okay, this is like this. Now we'll talk about the negative half cycle. In the negative half cycle, here the voltage is negative because the input will act like this. Because of this negative, this will be in forward bias. This will be in forward bias. So current will go to this. Current will go to this. Now current will go to the resistor like this and like this. Current will go, and at this stage current will go to this and will come like this. Okay. So in this case you are getting again the voltage drop, and at the output stage you are getting V0. So it means it is going to conduct in both cycle, positive and negative, positive half and negative half of one cycle. So if you'll read this, in the positive half cycle, D1 and D4 are in forward bias. D1 and D4 are in forward bias, as we have seen this, and D2 and D3 are in reverse bias. In the negative half cycle, D2 and D3, that is the negative half cycle, D2 and D3, here, these two will be in forward bias and D1 and D4 in reverse bias. The output voltage waveform is shown in the figure, and it is same as the full wave rectifier. See, you will get the full wave rectification. So in the negative half cycle, we have seen, we can check the polarity, whether we are getting at the same. In the positive half, we were getting voltage like this. In the negative half also we were getting voltage like this. Why? Because the current direction is, see, current will flow from positive to negative, right? So current will start from this side, and here it will get the positive. D2 will go to this side and D4 and will come out. So the direction is same. Current direction in both cases we are getting in that this way. So V0 will be same like this. So here also we have to calculate in the bridge rectifier. We are having a new concept or ripple factor. See, actually the main disadvantage is that it requires 4 diodes. It means if you consider the practicality of diode, you will be having voltage drop across 4 diodes unnecessarily. Means in one cycle you will lose 1.4 volt, because in one half you are encountered with 2 diodes, each 0.7 voltage drop. For 2 you will get 1.4 volt. So this is disadvantage. When low DC voltage is required, then secondary voltage is low and diode drop 1.5, as I told you. So the ripple factor is the measure. Here for the bridge wave rectification, we are having another concept, and that is the ripple factor. The ripple factor is the measure of the purity of DC output to the rectifier, and is defined as, this is the purity factor, can I say, ripple factor, and ripple factor is given by RMS value of the output voltage. You have to calculate the RMS value of the output voltage divided by average DC output voltage. Ripple factor is nothing but the RMS value of the output voltage divided by average DC output voltage. Okay. So this will be like V square RMS minus V0 square divided by V0. Okay. So this is like VRMS square divided by V0 minus 1. We are not going into the calculation because we need the output. Okay. So for the bridge wave rectification, see, we have seen 3 things: full wave rectification, half wave rectification, and bridge wave rectifier. In the bridge rectifier, we got the wave at the output like this. For the full wave also we get the similar one, but for the half wave we got like this. For full wave and half wave we calculated V average, and for BR we calculated ripple factor. Is it okay? Now come to the next one, and that is the clipper circuit. Okay, this is another application of the diode. So today we will start with the clippers. Clipper circuits are used to select the portion of the input wave which lies above or below some reference level. Okay, means in the circuit I'll show you. Some of the clipper circuits are discussed here. The transfer characteristics V0 versus Vi, and the output voltage waveform for a given input voltage are also discussed. So the first case of the clipper is clipper circuit 1. Is it okay? So first check the diagram of this. This is the clipper circuit 1. What we are going to clip? You are having, this is the input. You will clip it. Means some portion of this input wave if you want to remove, or you are using this in such application where you want the rippled output, or the clipped output. So you will use the clippers. Clipper means you have to cut your input wave at some point. Okay. See friends, this is the R connected with diode, and here one reference voltage is given over here. At this point you are calculating V0. At this you are applying the V input. Now how this circuit will work and why I am calling this clipper, you will know about this. Now come to the theory part. As we discussed, the clipper means it will clip if you have input like this, suppose positive half, negative half, you can clip it. Suppose you need this type of waveform, you can get it by clippers. Want to remove this portion? Yes, you can remove this portion. Or you can get this type of waveform also if you want like this. So you can clip it. Clip it means you can cut it. Is it okay? So the first case, the circuit shown in the figure we have seen, clips the input signal above a reference voltage VR. Our task is we have to clip the input voltage above VR, V reference. This is the output friends. Okay, this waveform is output waveform. This is the input waveform. Forget about this. Don't confuse yourself. I'll apply this in another way. I'll apply this that you have given with V in, and your V in is like this, whatever given over here. Let's take it Vm sin omega t. Okay, fine. Now you have to clip the portion above reference voltage. Let me change the color of the pen. One reference voltage will be given like VR. Your task is to remove this part. I don't need this part because at the output I need this one. I need this one only. So your task is to clip this part. How to clip this? How this circuit will clip it? Let's check it. Come to the part for clipper circuit 1. The circuit shown in the figure, and our task is to clip the circuit or the output above VR. So for that, Vi, if the condition is, this is the condition first, if Vi less than VR, diode is reverse bias and does not conduct, therefore V not equal to Vi. Let's see what is it. He is saying that if Vi, the first condition is if Vi less than VR. Now tell me friends, if VR is greater than Vi, means the potential at negative terminal is higher than the positive terminal. What is the stage of diode in this case? It will be in reverse bias. Reverse bias means you can open it. This is the useless in the circuit. If in this condition, if the diode is useless, your new circuit will be like R, here V in, here V out. Simply you are taking V out. Your V out is equal to the V in this case. Is it okay to you? When Vi is less than VR. In this case, the output is equal to V in. This is your condition. Okay. So in the first case we have seen if Vi less than VR, at the output we will get V0 is equal to V input. Let's come to the second condition, and second condition given as when Vi is greater than VR. Come to the circuit. If you will see this circuit, Vi is greater than VR, means potential over here is greater than to VR. In this case, this diode will be in forward bias. Is it correct? This is the condition given when Vi is greater than Vr. Is it okay? So friends, see, when this condition will be there, the circuit will be R. Here applied voltage is Vin. Okay, fine. The diode is short circuited because in forward bias. Here simply the battery VR, and this is nothing but your output. Now tell me what will be the output voltage. Directly VR is the output voltage between these 2 points and B. Is it okay? Let me change the color. So V0 will be VR or not? Means once you achieved this condition, your output will be VR throughout. Is it okay? Means, see, how we'll draw the waveform for this? Now I'm going to draw it, okay? Please see it carefully. This is your input. Okay, fine. The input, let's take it. This is the max value of input. And this is the voltage waveform, okay? Let's take it Vi equal to Vm sine omega t and something. Scale over omega t. This is one cycle given for the input. Is it okay? Now, we are going to draw the output waveform. Is it okay? So, the condition is the Vi means input is less than Vr. This Vr is the fixed, right? On the positive value, having some value, let me draw it. Waveform or for the line for Vr, okay? Here it's Vr. This is the Vr, constant quantity Vr. Is it okay? Now the question is, if Vr is less than Vi, if Vr is greater than Vi, for this term, for this is the Vi. Is it okay? This is Vi or not? This entire waveform is for the Vi. In this case, only from this point to this point, this condition is fulfilling, where Vr is greater than Vi. Correct? When Vr is greater than Vi, yes, in this condition, V0 is Vi. Output follows input. Means output will be as it is input. In this case only, let me draw over here also. When Vr is greater than Vi, the output will be same as input. So up to here, the input is this. So output will be this. Is it okay? Next, as Vi greater than Vr, in this condition, output will become Vr throughout. So this is the output waveform I'm drawing. So up to here, this is the condition where Vi greater than Vr. Is it correct? Means this point to this point. So up to this, the output will be constant Vr. Is it okay to you? Now for this entire thing, it will be same as input. Is it okay? Because this entire thing is Vi less than Vr. Okay, for Vi greater than Vr, the output is become Vr, and for remaining thing, the output is equal to Vin. So this is your output. Okay, so you clipped it. This much portion of the input waveform, you clipped it. This is you are getting at the output. I hope this is pretty clear to you. We'll see some problems, so all your doubts will be clear out. But before that, come to the second circuit. In the second circuit, the situation is same. I inverted the diode circuit. Is it okay? It's clearly visible over here. Let's see what will be the condition. Now, we'll be having two conditions. Once Vi greater than Vr, and second is Vi less than Vr. Let's see what will happen when this two condition will occur. In this condition, when Vi greater than Vr, means this terminal is at higher potential than this terminal. So the diode will be in reverse bias, definitely, because this one at higher potential than this. So it will be reverse bias. Reverse bias means you can open it. First I consider this case, right? So you can open it. So your resultant of the circuit will be like, you can open the diode circuit, it is useless. So Vi, here V0. So in this case, V0 follows Vi. In this case, V0 follows Vi, as you can see. I think it's pretty clear to you. It's very easy concept, right? In this case, V0 follows Vi. In this case, V0 will be equal to the Vi. What if Vi is less than Vr? If this is less than Vr, if Vr is greater than Vi, means at the positive terminal of the diode, the potential is higher than the negative terminal. So it will be in short circuit, means forward bias. So in that case, you will get output V0 is equal to Vr. Is there any problem? Tell me. No? So friends, see, now we have to draw the output. These are the two conditions for me to draw the output. Now I'll draw the output over here. Let's take me over here. Okay, fine. Let's take input waveform. Okay. This is Vi. Is it okay? Vi. Okay, fine. Here I'll draw the output. Let's take Vr given over here, and Vr is given positive. So I'll draw Vr constant. Okay. Now I have to draw the output, and I have to keep in mind these two conditions. When Vi greater than Vr, when Vi greater than Vr, where is the Vi greater than Vr? Over here. Is it okay? This is the condition for Vi greater than Vr, and the remaining condition is for Vi less than Vr. Now see, for Vi greater than Vr, the output follows input, means I'll start with Vr over here. Suppose the output is like this. Is it okay? This is the condition: Vi greater than Vr, Vi greater than Vr. Output is same as input. So for this, the input is this much. So output is this much, same as input. Is it okay? What about the next one? When Vi less than Vr. When Vi less than Vr means for this entire region, this region and this region, it will be constant Vr, means output will remain constant Vr. This will be your output stage. See, here you can see this. This is your output signal. I hope this is clear to you. The second point is also clear to you. Now I'm telling you one short formula or trick to remember this thing. Simply you can do it. See, if the diode is connected in this way, so you can remove the, the lower part of it. You can remove the lower part of it. Means if you have a circuit like this, this is your input waveform. Is it okay? Draw the Vr also. Draw the Vr on the line or the waveform. Okay, draw it. Now see the diode you are seeing from this terminal. You are seeing the negative terminal of the diode. Negative means you have to remove all values below Vr. Below Vr you have to remove, and you have to remain with this. This below value is gone out. Okay. Now instead of this, if diode is connected in this way, now you have to remove the positive values. See, in the last waveform, we remove, the diode is in this condition. Positive terminal you are looking from this point A. So you have to remove the positive part from the input waveform. Is it okay? And above VR, remember, this is our benchmark. This is a trick to remember this. No matter how you remember, you can use yours also. But please remember this, okay? Come to the third one. In the third one, we are using the circuit bit tedious, because we are using the case 1 and case 2 together. So this is the VI, R, D1 and D2. They are connected with VR1 and VR2. First reference voltage, second reference voltage. In this case also is asking for the V node. So what are the cases over here? See, to clip the input signal between two independent levels. Now we will clip the input between two independent levels. Means between VR and VR1 and VR2. We can choose the value of VR1 and VR2. Here he chose the value VR2 is greater than VR1. The clipper circuit is shown in the figure. We'll draw it later. First says the diode D1 and D2 are assumed ideal diodes. Okay, fine. And they are ideal diodes. For the circuit, for the clipper circuit, when the first condition is when VI less than equal to VR1. When VI over here, suppose assume the condition first, when VI less than equal to VR1. What will happen? Tell me. When this terminal at lower potential than this one, the diode will conduct. It will be in forward bias. You will get output. Means this will be short. Once this will be short, the output will be nothing but VR1 or not. Is it okay? Sorry, what is the condition? Condition is VR1 is greater than VI. Yeah, VR1 is greater than VI. It means this diode will be forward bias. When this will be forward bias, the diode will be forward bias. So output should be VR1, but let me check it. So yeah, this is VR1, okay. So at the output you will get VR1. In this case, you will get output as VR1. Now come to the next one. When VI greater than VR2. When VI greater than VR2. So the terminal over here will be at higher potential than this. And obviously this will be off at this stage because VI is higher than VR2. And VR2 is higher than VR1. So it will be negative bias. So D1 will be off. In this case, D2 will conduct and the output will be VR2. I hope it's pretty clear to you. But what if the VI is greater than VR1 but less than VR2? Please try to understand this one because this one is the important. And this one is the different from the previous two cases, right? Here, if VI is greater than VR1, okay, we'll consider over here in the diagram. Let me clear it. The condition is this is if VI is greater than VR1. If VI is greater than VR1, so this one will not conduct, okay, and less than VR2, and less than VR2. If less than VR2, then this will also not conduct. If both are not conducting, they are useless in the circuit. They are open circuits. If you will remove these two, you will be remained with R1 and this is V node, this is Vi. Output follows input. So we are having three conditions when you are using two parallel branches having diodes and reference voltage in this way. Now we will draw the output circuit. Okay, output waveform. Here I am doing, this is input. Let's take it Vi. And this is Vi equal to Vm sin omega t. Is it okay? Now friends, the first condition, please draw VR1 and VR2 over here also. Okay, let me draw it. Let's take this is VR1. Okay, VR1 and VR2 is greater than VR1. This is VR2. Let's take it like this. Here I'll draw the output. Okay. Now the condition, the first condition is when VR1 is greater than VI. VR1 is greater than VI. Here is the condition. For this reason, VR1 is greater than VI. So for this reason, you have to get output VR1. VR1. For this entire thing, you have to get value VR1. Okay. For this tiny reason, this reason, you get the value VR1. Okay, fine. Come to the next, when Vi is greater than VR2. When Vi is greater than VR2. Here is the VR2 and this is the condition Vi greater than VR2. In this case, the output is R2. Okay, fine. So this is over here. Suppose let's take it over here. It's like this. So in this case, the output is VR2, VR2. Like this. Okay. Like this. VR2. And if for the below reason, for the below means for this condition, for this entire waveform, below VR1, the condition VR1 is greater than Vi satisfied. So it will be VR1. Okay. What about this? The reason in between VR1 and VR2. In between VR and VR2, the output follows input. So the circuit or the waveform will be like this. Is it clear to you? You are getting this one. Okay. This is the condition where VR1 is greater than Vi. First condition. And the second condition, the Vi should be greater than VR2. In that case, you are getting only VR2. And remaining reason, you are getting input. So this is your waveform. I hope it's very clear to you. This is the Clipper circuit all about. Okay. Now, in the next, we will solve some Clippers problem. So all doubts will be clear out there in the next class. Okay. So this is all about today's. We'll meet in the next. And one more thing I would like to tell you, friends, please maintain your pace with me. Please maintain a good notes so you can, recall it. Otherwise, after 1 month, it will be clear out from your mind. Okay. So we'll meet in the next and we'll solve some problems on Clippers. Till then, take care and bye.